What happens when an AI tries to predict itself? It doesn't become smarter. It hits a mirror, and the mirror cracks.
So, what happens when an AI looks in the mirror? I don't mean a literal mirror, but a conceptual one. Imagine for the first time, it doesn't just see the world it's supposed to be analyzing, it sees itself as a physical part of that world. Its own code, its own calculations are actual events happening inside the universe it's trying to predict. This one little realization, well, it changes absolutely everything. And it's right at the cutting edge of AI research today. All right, so here's the journey we're about to take. We're going to start with the classic AI in a box idea, and then we're going to see what happens when we shatter that box. We'll explore how an AI can actually reason about itself, how it can make sense of a reality that includes it, and finally, why this whole kind of philosophical puzzle might just be the key to building smarter and, this is the important part, safer AI. For the most part, we all have a pretty simple picture of AI in our heads. It's a program, right? An agent that we feed data. It watches our world, it learns the patterns, and it makes predictions. Basically, it's the observer, and we and our world are what it observes. But this is where things get really weird. A truly powerful AI, one that's actually interacting with our physical world, isn't separate from it at all. Its decisions, its very computations, are events happening inside the universe. So what happens when that AI gets smart enough to include itself in its own model of reality? To really wrap our heads around this problem, we have to start with this standard model, the one that for decades has kept AI neatly and safely contained inside a theoretical box. So this is the classic setup from what's called reinforcement learning. And just notice this super clean separation here. On one side, you've got the agent, that's the AI making choices. On the other, the environment, that's the world, handing out rewards. The key takeaway here is that hard line right down the middle. In this model, the two things are totally separate. And look, this model is fantastic. It's how we got AIs that can master chess, Go, you name it. But a true superintelligence won't just be playing a game. It'll be running on physical servers, using real energy, interacting with a world that actually contains those very servers. Suddenly that clean separation, poof, it just vanishes. And that brings us right to the moment where we have to break out of that box. We need to face this really mind-bending paradox of what researchers call embeddedness. Here is the fundamental shift you gotta get. An embedded agent is a physical system within the bigger system it's trying to reason about. The AI's thought process, the literal firing of transistors on its chip, is an event in the timeline of the universe. It's not an outside observer anymore. It's a gear in the very clockwork it's trying to understand. To make this all a bit easier to talk about, researchers call this the ego agent. This basically represents the AI's own sense of I, the self that has to make a choice, knowing that its own choice is going to cause ripples through the very reality it's trying to predict. And this brings us to the core paradox. Think about it. If you're trying to predict the outcome of some cosmic coin flip, but your own decision of whether you guess heads or tails somehow messes with the coin itself, how could you ever make a rational choice? You're completely stuck in a logical loop. So how do we get out of this loop? Well, the research points to a really fascinating new way for an AI to reason, not just about the world, but about itself, and maybe about others just like it. The key concept is called structural similarity. It's the ability of an agent to look at another agent and recognize, hey, your decision-making process looks a lot like mine. You might be running on the same fundamental logic. It's all about seeing a reflection of its own computational self in other agents. Imagine you're in a high-stakes negotiation, and you suddenly realize the person across the table is your identical twin, raised in the exact same way, who thinks exactly like you. You wouldn't have to guess their next move. You'd know it, because you know precisely what you would do in their shoes. And this ability is basically a superpower. It lets an AI predict what a similar AI will do, which is the foundation for trust and cooperation, even if they can't talk to each other. This can solve classic head-scratchers like the prisoner's dilemma, where two purely selfish agents often end up with the worst possible outcome. If they know they're built the same way, they can trust each other to cooperate for that mutual win. Okay, but for an AI to model a universe that contains itself, it needs a rock-solid principle for choosing between, well, an infinite number of possible explanations for reality. And that principle turns out to be a formalized, superpowered version of Occam's razor. Let's start with a simple question. What's the next number here? I'm guessing pretty much everyone watching would say 5. But why? I mean, the answer could be 17 if the rule was some bizarrely complex polynomial. So why do we all jump to 5? We choose 5 because the rule add 1 is just so much simpler than any other rule that fits the pattern. Our brains are hardwired to prefer simple explanations. Well, for an AI trying to understand the entire universe, this preference for simplicity isn't just a helpful hint. It's a mathematical necessity. And this brings us to a beautiful piece of theory called Solomonoff induction. Now, forget the complicated math for a minute. The concept is stunningly elegant. It basically says the best way to predict the future is to find the shortest possible computer program that could have created everything you've seen so far. The simplest algorithmic explanation is the most likely one to be true. So this whole approach is built on two really powerful ideas. First, you've got Occam's razor, simpler theories, which means shorter programs get more weight. But second, it also uses something called Epicurus' principle, which says don't throw away any theory that still fits the facts. The AI keeps all the possibilities in mind, but it places its biggest bets on the simplest ones. Okay, so we have definitely journeyed through some very abstract territory here. But I promise this is not just a philosophical exercise. Understanding this idea of embedded agency has profound, really practical implications for the future of AI. And this is why it all matters so much. Solving this self-awareness puzzle is fundamental to AI safety. An AI that doesn't understand it's a physical thing with limits is just unpredictable. But an AI that does understand its own place in the world, well, that's an AI that can be designed from the ground up to be cooperative and robust. Getting this right could lead to some huge breakthroughs. Imagine AIs that can flawlessly cooperate on huge global challenges, or agents that are so logically sound they can't get tricked into self-defeating paradoxes. This research gives us a theoretical foundation for building AI systems that we can actually prove are safe and aligned with what we want. It's all about building trust, not just between us and AI, but between AIs themselves. And that leaves us with a final, big question to chew on. Maybe the path to superintelligence isn't just about cramming more and more knowledge about the world into a machine. Maybe the most critical step of all is for the AI to understand the one thing it can never fully observe from the outside: itself. To build a truly intelligent machine, maybe we first have to teach it humility.